Now I'm going to try to relate the connection between a logic gate and a transistor. So let's say our goal is to design a logic gate. I don't know which logic gate it is going to turn out to be just yet, but my goal is to design a logic gate using a transistor. So uh, let's take the approach of, say we have one transistor, in this case Q1. Let us provide an input to it. Let us see what the output is going to be. And by monitoring the state of the input versus the output, we will see what that logic gate turns out to be. So let us try to zoom in on this simple BJT based circuit. We have Q1, which is essentially a bipolar junction transistor with three terminals: B for base, E for emitter, C for collector. We are controlling the base voltage by using a voltage Vx, and we are monitoring the collector voltage as Vy. We are using a pull-up resistor, which is essentially a resistor to pull the voltage up to 5 volts. So pull-up resistor. And we have connected the emitter to ground. That pull-up resistor is, right now it doesn't really matter, but it is R, say 1 kilo ohm resistor. And we have some resistor at the base of the transistor, and let's say it is a 1 kilo ohm resistor. That is essentially going to be limiting the current that flows into the transistor. So what is going to happen when you have uh, the switching states at the input? What is going to happen at the output? So to be able to monitor these, we have a table on the right side. We are monitoring the voltage at the base of the transistor Vx. Note that Vx is split between VBE, which is the voltage at the base with respect to the emitter, and also the voltage across the resistor here. So I'm talking about Vx to be a voltage in two cases, low and high. So let's say I have two possibilities. Voltage at the base, I could use a low voltage, I could use a high voltage. I'm monitoring the state of the transistor on and off, and I'm also trying to measure Vy, so the voltage at the collector with respect to ground. So let's see how this is going to how we can fill this table up. So when we have a low voltage at the base Vx, Q1 will not get enough voltage to turn on. So in this case, Q1 is going to be off, meaning the collector and the emitter terminals have an open circuit between them. If there is an open circuit between the collector and the emitter, then Vy does not have a path to ground, which means Vy is not going to equal 0 volts. In fact, now it is going to measure a high voltage because it is being pulled up by that pull-up resistor. So Vy is going to measure high in this case. Now in the other case, and the other row here, when Vx is high, we have enough voltage to turn on Q1. So the state of Q1 is going to be on, in which case we have a short circuit between the collector and emitter. So Vy is going to be essentially at the same potential or at the same voltage as ground. So this is going to be low. So it turns out when we gave a input of 0 and 1, we got an output of 1 and 0. So this would make this gate a NOT gate. So that means this diagram is representative of a NOT gate. So we have essentially designed a NOT gate using a transistor. Okay, so that was one. Now the question is, how do we design, say, a buffer? Buffer, what does that mean? I need y equals x, right? Input equals output. How do I do that? Well, the simple way to do this is to have two NOT gates connected back to back. So what I'm going to do is I'm going to take one transistor and I still have the pull-up resistor to say 5 volts, and this is my Vx. This is the base, this is the collector, this is the emitter. So far I have one NOT gate. I need two of them. So what I'm going to do is I'm going to copy this guy and paste it in such a way that I connect it there. So I have taken the output of, so let's call this a certain point. Let's call this V out 1, and my final output is going to be V out, and in fact we can call this V in. So we have two NOT gates. The output of the first NOT gate is feeding into the input of the second NOT gate, and we are actually monitoring the output or the collector voltage of the second transistor. So that's going to be equivalent to placing two NOT gates back to back, which is going to give us the buffer. So in this case, V out. So if I build a table with V in, V out 1, and V out, I'm going to have 0 becomes a 1, becomes a 0, 1 becomes a 0, becomes a 1. So goal is these two are the same. So that's how we are going to build a buffer. And as you can see, we needed two transistors to build a buffer, but earlier we only needed one transistor to build a NOT gate. Okay, let's move on here to an AND gate. How do we design AND gate? So I hope you remember from our earlier discussion, we need switches to be in series. So that was the key idea of AND functionality. So let's see if we can put some switches in series and develop a AND gate, design an AND gate. So I need, say I have a two input AND gate to design. So my goal is to design an AND gate with two inputs. Let's call that x1 and x2, and my output is y, say. So how can I do this? I will be able to do this by having two transistors, and I need them to be in series. So let me draw transistor 1 over here and transistor 2 over here, and I have connected them in series. Their base voltages are being controlled by voltages Vx1, Vx2 that are representative of binary inputs x1 and x2. Let's see. I have connected the emitter of the second transistor to ground, and I have pulled up the collector voltage to 5 volts. So now I have Q1, Q2 as two transistors. Let's 1 and 2 transistors, and I am monitoring the output at the combination of both of them in series. So that's my VY. So I've placed switches in series, transistors in series, and right now I think that this will work as an AND gate. Let's see if it does. And I'm still pulling the voltage up to 5 volts using the pull-up resistor. Say this is R. All these resistors can be 1 volt for our discussion. Let's see. Let's analyze this circuit. We can do that quickly by monitoring Vx1 and Vx2 as two input columns. We have Q1 and Q2 as the state of the transistor, and we have Vy as the output. So because I have two inputs, I'm going to have low, 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 high, high, low, and high, high as the four possibilities between these two voltages. And if the base voltage for any transistor is low, then it is going to be off. So I have off, 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 on, okay, on, off, on, here. Now, as you can see, Vy will be high most of the time. It will only be able to be pulled down to ground in the case when Q1 is on and Q2 is on. Only then it will be connected to ground. So the only output that is going to be off is going to be when Q1 and Q2 both are on. So this is going to be off only there. But otherwise, because one of them is off, 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 Vy is going to be reading, oh sorry, not off, I should say low. It is going to be connected to ground only, it is going to read 0 only when Q1 and Q2 both are on. Otherwise, if any one of them is open or off, it is going to read high, high, high. Now, if I observe this output, it looks like high, 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 low, which is exactly the opposite of the AND function, which is low, 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 high. So this, in fact, is a NAND gate. So I'm going to have to adjust the symbol accordingly. I have a bubble in the front. So this is performing the operation of x1 and x2, and then there is a bar one. So we tried to design AND, but in fact we designed a NAND function. So for a two input NAND, we needed two transistors. For a three input NAND, we would need three transistors in series, and so on. Now let us see, we still need to figure out how to design AND. So let's try to build AND over here. So for this, I need NAND plus NOT. So if I have NAND plus NOT, so imagine this. I have, say, NAND here and NOT here. The bubbles, because there are two of them, will cancel out, which means I have the equivalent of that is going to be AND. Double negation. So by using that concept, we can build AND gates by using NAND gates and NOT gates. So for that, I'm going to borrow this particular circuit diagram, paste it there. I also need NOT. So I'm going to go back and borrow my NOT function and paste it there. Hopefully it I can no longer call this Q1 because I've exhausted Q1. Let's see what else will change. Nothing really. So I've got Q1, Q2, and let's call this as Q3. I have V out 1 here, and I've got Vy finally. So my final output is right here, and my two inputs are here. So in this case, Y is going to equal X1 and X2. And sorry, NAND followed by NOT will give us AND functionality. So nothing specifically like an AND function, we'll have to build it using two other logic gates. How many transistors do we have in a two input AND gate? How many transistors? We have got three in this case. Three transistors. Two to do the NAND function, one to do the NOT. All right, let's move on and talk about, so we talked about AND already. Let's talk about NOR. So if I have switches, let's see, is there a difference between a transistor that we are using now to make these circuits compared to a switch, which is what we are using before? So a switch is going to be in a two-state element, on off. So we can look at, we can see the transistor is not just going to work as a switch, but it's also going to work as a current amplifier. So the transistor has more capabilities than a simple switch. But for the discussion on logic devices, logic circuitry, we are going to assume that the transistor is operating in those two extreme cases, when it is on and when it is off, meaning it is in the either in the cutoff region or in the saturation region. So the difference is only that we are sort of ignoring the active region of the transistor in all these conversations. So now let's see how do we build a NOR gate. In the NOR gate, we needed what? Transistors in parallel or switches in parallel. So we have one switch over here, which is the base voltage is controlled by X1. The base voltage for another parallel uh, transistor is controlled by Vx2. They are both in parallel because both the collector terminals is where we are measuring Vy. We still have one pull-up resistor going to 5 volts. We have both the emitters connected to ground. So I can read, I will be able to read Vy as low when Q1 is on or Q2 is on or both are on. So Vy will be 0 or low when Q1 is on, Q2 is on, or both are on. And they are on when Vx1 and Vx2 are high. So when they are high here, here, or here, it is going to read ground. Only when they are both transistors are off, Vy is going to read high voltage, because there is no pull down network. But there is a pull up resistor R1 to pull up the voltage of Vy to 5 volts. So NOR, a two input NOR we need two transistors that are in parallel. And as you might imagine, to get OR functionality, we just need to attach a NOT gate in front of the NOR. Okay, so if I wanted to say build OR, all I would do is one transistor here. Let's not put that. Okay, one transistor here, another transistor over here, both connected to ground, emitters connected to ground. We have two inputs. Um, this is R. One pull-up resistor, 5 volts. Uh, take the output from here and feed it into a NOT gate. So that is going to give us OR. Let me write the inputs as Vx1, Vx2, and finally I have Vy. So just for the sake of clarity, I am going to say this is going to be one gate and that is one gate. So that's NOR and this is NOT. One after the other gives us OR gate. So this is a two input OR gate. If we had a three input OR gate, then we would have one more transistor in parallel over here. We still need the NOT functionality. All right. That sort of completes our discussion on switches, transistors, and uh, logic gates. Let us see if I missed anything that I wanted to talk about here. We are going to do this later on. Okay, I think we are okay. Let me stop the recording with this.